Today we are gonna do another question, which is find relation of sound. Relation of speed of sound that depends on elasticity, elasticity, E, and density of medium, which is represented by rho. So we have to find the relation between this speed of sound, which I will represent here in by s in this case, or you can represent it by v. I'm gonna do it by s over here to show that I can represent in various ways, but it will be better if you represent it by v. So the dimension of speed of sound, so which I'm going to represent by s, or you can represent it by v. So if you're going to actually represent it by s, you will have to formally write it out, since there is nothing present that states that s will be the speed of sound. So the dimension of speed of sound, which will be s, must be lt minus 1, and the dimension of elasticity will be ml minus 1 t minus 2, and the dimension of density will be ml minus 3. Since elasticity, the most common formula of elasticity will be using the Young's modulus, which is stress over strain, and strain is a dimensionless quantity, and strain is actually force upon area, which will mean the dimension of elasticity will be the same as the dimension of Young's modulus of elasticity, which means that it will be the same as the dimension of stress over strain, which means it will be the same as the dimension of stress, which will be the same dimension as force upon area, which will have the same dimension as pressure. So this will be the dimension. So let's make a quick note over here. Young's modulus is stress over strain, um, and stress is force upon area, and this is dimensionless. So this is a quick note when doing of um, elasticity, and there are several types of elasticity. I'm just talking about the one that we learn about in this course with later on. So now we have the terms. Now let's start the thing. So we have, since the speed of sound depends on elasticity, we don't know to which power, let's suppose A, and density, let's suppose it depends on the power raised to B, we will get this. To remove the proportionality sign, we need to add a proportionality constant, let's suppose it is K. So now, where K is dimensionless proportionality constant, I'm writing dimensionless over here. So now when I'm gonna write the dimensions of, so that's why I didn't write the dimension of k right over here. If I wrote the dimension of k right over here, I would not write dimensionless, or it would not have mattered if I wrote dimensionless or if I didn't write dimensionless. But it's just formal language. It's when you're doing calculation for fun or just for yourself, it's not that necessary to use formal language, even though I highly recommend to use formal language, or at least shorthand notations of formal language to make it easier for you. So that if the relation is valid physically, the dimension of left hand side must be equal to the dimension of right hand side. So the dimension of speed of sound must be equal to the dimension of k e raised to the power of a, rho raised to the power of b. So that means the dimension of speed of sound, the dimension of k, it is dimensionless, so it will be dimension of e raised to the power of a, dimension of rho raised to the power of b. So let's add the dimension of each term, which will be of speed will be lt minus 1, elasticity will be m l minus 1 t minus 2 raised to the power of a, and density will be ml minus 3 raised to the power of b. So in this case, even though I used s for the symbol of speed of sound, it will be much better if you use v, since small v is generally considered the symbol that is used for speed of sound, and it will have less confusion when you use that symbol. So here we have m0 lt minus 1, which will be equal to m a plus b l minus a minus 3b and t minus 2a. So we are just raising the power by these exponents, and we are using the laws of indices to add them up. So now we have to equate the power. So equating power of same base on both sides, we get, so let's go back to see the equation. So 0 must be equal to a plus b, so a plus b must be equal to 0. Let's call this equation 2, and actually I forgot to write the equation 1 right over here, so let's make this equation 1. And also here minus a minus 3b must be equal to 1, since L raised to the power of nothing means it is raised to the power of 1, since we generally don't write when it is raised to the power of 1. So minus a minus 3b is going to be 1. So equation 3. After that we have minus 2a minus 3b must be equal to minus 1. So let's go back. So minus 2a, wait a second, I seem to have done a mistake, so it's just minus 2a. So minus 2a must be, let's go back. Yep, so elasticity is m l minus 1 t minus t minus 2. So we have this. So minus 2a minus 2a must be equal to, wait a second, so let me pause the video, I'm actually confused. Yeah, okay, I checked it out. Yeah, it's right. It's minus 2a must be equal to minus 1. I did not see the minus 1. I thought this was a 0. I was thinking, how can it be 0? So it's minus 1. So this will be our equation number 4. So on solving is pretty trivial. So from equation 4 we get a is 1 half. A is 1 half. Now you can use any of the equation. You can use this or this one, which will lead you the same answer. So let's use this one. Then I will also use this one. So here we will get 1 half, which means b will be minus 1 half. Or if you go here, it will be minus 1 half plus minus 3b equals 1, which will also leave you with minus 1 half. So um, now, so we have both the values of a and b. So let's use equation 1. So from equation 1, we have s, which is k times e raised to the power of a, which was 1 half, and rho raised to the power of b, which is minus 1 half, which means s must be equal to k times square root e by rho, which is the physical required relation between the physical required relation between speed of sound, elasticity, and density of medium. So that was it for today's video. In the next video, we are actually gonna do something big, which is actually start a new chapter. So I think the new chapter is gonna be vectors. I'm not sure. So be ready for that video. Till then, bye bye.